So this is the analysis for the rocket, and I shot two rockets, and the first one I shot was blue, and the second one I shot was yellow. And the example calculation I'm going to give for this blue rocket, it had an engine called B4 in it, and the first 4 is the thrust in newtons, and the second 4 is the deploy time in seconds, 4.0 seconds. The yellow one had an engine B64 in it, which means that the thrust is 6 newtons, and I will call it actually 6.0 because and 4.0 because in the instructions on these 10 laps for the rocket, I mentioned that I like it to use 2 significant figures, so I'll do that here as well. So the deploy time here on the B64 is also 4.0. The burn time, I actually had to look that up elsewhere, is 1.1 seconds for this one and 0.8 seconds for this one. Okay, the rocket masses, I measured them before I shot them, which was good because we had so much wind on that day that we shot them that we lost them both. So this was 64 grams, which of course is 0.064 kilograms, and this one was 0.061 kilograms, 61 grams what we measured. Okay, so as I said, for this one now I'm gonna calculate all this here, and then you have to calculate yourself this one here as you are going to the 10 laps for the rockets. Okay, the acceleration is written on the next page in the guidelines, and here it is, equation A. There it's the net force in the numerator divided by the mass of the rocket. Mass of the rocket is of course 0.064 kilograms for my example for the blue one. And then the thrust I just wrote down, and then here is the weight, mass times negative 9.8. The thrust is positive going up, that makes sense, and the weight is negative going down because gravity likes to pull the rocket down. There's air resistance here, however I could never figure out how I could compute or measure air resistance, so I'm actually leaving it out. That introduces a huge error. If you can imagine that if in the theory I leave out the air resistance, then the rocket theoretically is going up very high without air resistance, but in actuality when we actually shoot it, of course there is air resistance, and it's definitely not gonna go that high, in fact appreciably lower. So because of that there is a huge disconnect between the actual measurement and the theory, which is what I'm doing now. But I learned to live with that large error, and again I just want to point that out. So here's what I'm going to calculate. The acceleration equals thrust minus the weight divided by mass, leaving out the air resistance. So what I'm going to calculate now, or it's exactly what I'm going to calculate. Okay, so that's going to be, the thrust was 4 newtons on the blue rocket, the B44 engine, so plus the mass of 0.064 kilograms times a negative 9.8. So there's that negative, the weight pulling it down, close the parentheses, divide by the mass 0.064 kilograms, and that gives me the acceleration of around at 53 meters per second squared. So there it is, 53 meters per second squared. So that's how fast it accelerates, about 5 times as much as what gravity tries to pull it down, if you compare 9.8 to 53. Okay, next is the thrust velocity. That is calculated with this equation. So thrust velocity is simply the acceleration I just calculated times the burn time. So 53 times the the burn time just off the screen here times 1.1. So 53 times 1.1, and actually I'm not going to do that. I'm going to use the exact number here, 52.7 times 1.1, so that all the intermediate results, they have more exact numbers. The end result is just going to be the only one is going to be rounded as well. So that's 58 meters per second is the thrust velocity. That's when the engine is expired. That's the end velocity with which it then keeps rising. The thrust height, that's how high does it go during the thrust phase, and that equation is given here. The thrust height, 1/2 times the acceleration times the burn time squared. So 1/2 times the acceleration times the burn time squared. 1/2 times 52.7 times 1.1 squared. There we go. 32 meters. 32 meters of thrust height. Okay. Then it keeps rising because of its thrust velocity at the end of 32 meters up or 100 feet up without the air resistance again. It has a velocity of 50 meters per second up, so even though the engine is done now, it keeps rising because it has a large velocity. So I'm going to calculate the height with which it go up. I used to calculate what is the free fall height. However, at some point the parachute is going to deploy, and the parachute usually deploys before the rocket reaches the highest point, so that's what I'm going to calculate. So the equation for that is this long one here. So the parachute height after the thrust phase is over is 1/2 times negative 9.8, because of course gravity tries to pull it down, times the deploy time squared, that's the 4 squared, plus the thrust velocity times the deploy time, which of course again is 4 seconds.